Okay, welcome to part 4 of our lecture, that is 2A in this module. Alright, let's start actually talking about what happens here. What are the greenhouse gases doing at different wavelengths? What are their monochromatic properties that make them have this effect on the energy budget of the Earth? And remember, we use this powerful vocabulary word of selective absorbers to explain these materials. And what I want to do is I want to show you a diagram here that comes from a fairly advanced textbook that shows over a range of wavelengths. Notice that the x-axis of these diagrams is wavelength. So this is a range of different kinds of radiation, but these are all long wave types of radiation here. And you can see over a range of wavelengths, different materials. You can see carbon monoxide, methane, nitrous oxide, ozone. Ozone actually is a greenhouse gas too, somewhat confusingly. Carbon dioxide and water vapor, as well as all of them added up, they have different properties. Now this property that you're seeing on here, that is actually transmittance. It is how much of the radiation gets through the atmosphere of those gases there. And that range of wavelengths there that I have highlighted from roughly 1 micron to about 16 microns is just part of the full electromagnetic spectrum of radiation, where shortwave radiation is stuff like visible light, ultraviolet radiation, and so on. But long-wave radiation, the kind of stuff emitted by like the surface of the Earth and greenhouse gases and clouds and so on, is like infrared radiation, microwave radiation, and so on. This chunk of the electromagnetic spectrum of radiation is a part of the electromagnetic spectrum where the Earth, at the rough temperature of the Earth, is, roughly 300 Kelvin, or about 20 Celsius, which is what, about 58 Fahrenheit, something like that. 68 Fahrenheit. The average temperature of the Earth. Well, if you actually take a look at a graph, like what's up there in the top left, of how much radiation the Earth is emitting at those wavelengths, so you can see at different wavelengths, different on the x-axis there, you can see that the Earth emits some radiation at like 5 microns, a bunch of radiation at like 10 microns, somewhat less at 15 microns, and so on. This happens to be the range of wavelengths that the Earth emits a lot of radiation. So we're going to be trying to combine the information from these two graphs here. We have information that shows on this one graph that shows like the monochromatic absorptivity and transmissivity of different gases in the Earth's atmosphere. We're going to be focusing on the transmissivity, the ability of the radiation to get through all that carbon dioxide, the ability of the radiation to get through all of that water vapor and so on, or methane or whatever. And we're going to be comparing that to what the Earth actually emits. And what we're going to do is take this little piece of this diagram here that is the collective absorption, that is all the greenhouse gases added together, and that graph that showed all of the radiation the Earth's surface was emitting. And what I've done here in PowerPoint is sort of stretch them and distort them until the scales matched. Okay? So the top diagram there shows how much radiation the Earth's surface is actually emitting at each of these wavelengths. And then the bottom diagram there, the sort of stretched out thing, is how much of that radiation is actually being transmitted through the Earth's atmosphere. Okay? So we can put these two pieces of information together to start figuring out, well, let's see, if the Earth is emitting this long wave radiation, what's happening to it once it starts trying to go through that big, thick, gooey atmosphere of the Earth? Well, we'll take it apart kind of piece by piece. Like right now I've highlighted there in blue a range of wavelengths between about 8 and 13 microns or something like that. And it happens to be the range of wavelengths where the Earth is emitting a lot of radiation. The total amount of radiation the Earth is emitting in those wavelengths is sort of the area under the curve in that range. And that's a big amount of radiation. That's the biggest chunk on that graph. So the Earth emits a fair amount of that kind of radiation, and in fact if you then extend that down to the lower panel that shows what actually makes it through the Earth's atmosphere, you see that the transmissivity of the atmosphere at that range of wavelengths is actually pretty high. The Earth is emitting quite a lot of radiation at those wavelengths, and yeah, some parts of it it, it's like near what is about 9.5 microns, and near again about 13-ish microns and so on. There are some wavelengths where the monochromatic transmissivity of the Earth's atmosphere is not very high, and some of that radiation is being stopped, but most of it's actually getting through. This is an important part of the electromagnetic spectrum. It's called the atmospheric window, a term that every atmospheric scientist hates. Because the atmospheric window isn't a place, it isn't a thing. The atmospheric window is a range of wavelengths, between about 8 and 13 microns. There's different definitions of exactly what wavelengths there are. But it's a range of wavelengths of long-wave radiation that happens to be a range of wavelengths the Earth emits a fair amount of. And, as it happens, it's generally transmitted through the Earth's atmosphere. By and large, that radiation escapes directly to space and is not absorbed by carbon dioxide, water vapor, etc. Maybe a little bit, but by and large it gets through. Changing the amount of carbon dioxide in the Earth's atmosphere, or methane in the Earth's atmosphere, won't really all that significantly change that, because those gases don't really affect radiation in that range of wavelengths. So this is, going back to that diagram from NASA there, this is the heat that is able to directly escape to space. Of the 240 watts per square meter of long-wave radiation that is emerging from the top of the Earth's atmosphere and headed out into space, that a satellite can see and so on, about 40 watts per square meter is radiation that is passing through the atmosphere, is radiation and wavelengths associated with the atmospheric window. This is a very efficient way to get energy out of the Earth atmosphere system and back out into space. Okay? But there is so much else going on this diagram that we're looking at here. For example, let's look at two other ranges of wavelengths. They happen to be between like 5 and 7 microns, and then another one between like 13 and 16 microns or whatever. But again, if you take a look at the top panel of diagrams there, the diagram there, you can see, if you're thinking about this in terms of being like the amount of energy that the Earth is actually emitting at those wavelengths as being the area under the curve, well, in those two ranges of wavelengths, the amount of radiation is pretty high. I mean, it's not as high as it was in that middle one, but it's still pretty darn high. So the Earth actually emits a fair amount of energy, a fair number of joules of energy per square meter per second is being emitted at ranges with wavelengths of radiation between, that fit in those ranges. But if you extend those blue ranges down to the matching parts on the lower panel there, that shows how much of that actually gets through the Earth's atmosphere, it's zero. Basically, none of the Earth's radiation at those wavelengths actually makes it through the Earth's atmosphere out into space and that gets lost. That radiation is almost completely absorbed by greenhouse gases in the Earth's atmosphere. With the amount of those greenhouse gases we already have, adding more greenhouse gases to the Earth's atmosphere can't change that, because we already absorb it all. You can't absorb more than all of the long-wave radiation, right? So just like in the atmospheric window, where adding more greenhouse gases didn't really make a difference because those greenhouse gases don't absorb that radiation anyway, we're not going to change how much gets away through the atmospheric window. At these ranges of wavelengths, which strangely don't have a name, like atmospheric window, which would be handy, the atmosphere already transmits basically nothing. That radiation is trapped by the Earth's atmosphere, absorbed by greenhouse gases, and gets re-emitted back down toward the surface of the Earth. Increasing the amount of greenhouse gases does not change that at all. So this is heat that is not able to escape, turning back to that NASA diagram here, this is heat that is not able to escape to space. It's absorbed by the atmosphere, and then those greenhouse gas molecules emit it either up towards space or down towards the ground. By the Stefan-Boltzmann law. Oh, okay. So far we've kind of picked apart some chunks of the electromagnetic spectrum and seen how the emission of them and transmission of them is affected by greenhouse gases. And so far we found out that, yeah, greenhouse gases play a role, but none of the parts of the spectrum we've looked at so far would changing the amount of greenhouse gases affect what's going on. But that's because there's still more to look at. For example, here are 3 more ranges of wavelengths of the electromagnetic spectrum. What is it? From like 4 to 5 microns, and 7 to 8 microns, and 13 to 14 or something. Again, I wish they had names for these bands, but as far as I know, they don't. But again, you know, if you look under the area, under those curves, in those ranges, a sizable chunk of the total amount of energy the Earth is emitting comes from those ranges of wavelengths, because it's under that curve. The Earth emits a lot of joules of energy in the form of electromagnetic waves with these wavelengths. And if we extend the diagram down again to the corresponding parts of the graph that talk about the transmissivity of the atmosphere to those wavelengths, what you find at those ranges of wavelengths is that the transmissivity is neither 100%, and it all gets through, nor is it 0, like none of it gets through. It's in between. There's some place, you know, at some exact wavelengths, the radiation is, the monochromatic transmissivity is a little higher, at some it's a little bit lower. With the amount of greenhouse gases we have in the atmosphere now. So there's stuff in the Earth's atmosphere that can absorb this kind of radiation. The radiation of these wavelengths can be absorbed by that stuff. And if we had more of that stuff, we would be absorbing more of that radiation. Less of it would be transmitted out into space. Okay, well, this doesn't tell us what the stuff is in the atmosphere that's actually doing that absorbing, but the rest of this diagram that comes again from a more advanced textbook kind of gives us that information. I mean, instead of looking at the bottom panel, which is the adding together the effects of all the greenhouse gases, if we separate it out into what are the effects of carbon monoxide, and methane, and nitrous oxide, and ozone, and carbon dioxide, and water vapor, well, we can actually get all that information separately for each of these gases. And if we take a look at those same 3 bands highlighted in blue that are the ranges of wavelengths we're thinking about as being kind of odd, that they're the ones where the total atmosphere absorbs some, but not all, of the radiation in that wavelength, and you start looking across those individual constituents, you can see that carbon dioxide, which I've highlighted there in black, is responsible for some of that absorption. Carbon dioxide has monochromatic absorptivities at certain wavelengths that are absorbing some of that radiation. And if we had more carbon dioxide in the atmosphere, it would be absorbing more of it. Well, so as actually are some of these other greenhouse gases we worry about. Like highlighted in green there, I've got the parts of the electromagnetic spectrum that are being absorbed, at least partially absorbed, by nitrous oxide, or by methane, or water vapor, and clouds, and so on. These are wavelengths of radiation that the Earth is pretty good at emitting, and the atmosphere absorbs some of it, and some of it gets transmitted with the relatively small, we have concentrations of carbon dioxide in parts per million. In methane, it's parts per billion. If we increase those gases, they will be absorbing more of this. They will be able, so these greenhouse gases are absorbing some of this radiation at their current concentrations. If we increase the concentration of those gases, they will be absorbing more of the long-wave radiation at those wavelengths, keeping more of the radiation, long-wave radiation that was emitted by the surface of the Earth from getting out into space. Oh, that is not good. That would be this chunk, again, turning to the diagram from NASA here. That is that chunk of heat that is being absorbed by gases in the atmosphere. I've it highlighted in red on the diagram there. And then those gases themselves will emit long-wave radiation by Stefan-Boltzmann law, both up towards space and down towards the surface of the Earth. Uh-oh. See how these greenhouse gases have this problem? It's not that they absorb all the radiation getting out from space. We have gases that do that. In fact, they are greenhouse gases too. The issue is these parts of the electromagnetic spectrum where we are currently partially absorbing that at the current concentrations of the greenhouse gases. If we increase the greenhouse gases farther, we are trapping more and more of that long-wave radiation, keeping it from getting out into space and further tampering with the Earth's energy budget. These greenhouse gases absorb long-wave radiation that was emitted by the surface. They emit long-wave radiation themselves. That long-wave radiation might be going out into space, but might be going down towards the surface of the Earth as well, where it'll get absorbed and increase the temperature of the Earth. And these greenhouse gases, we know that by increasing the concentration, we are increasing the greenhouse effect. The right word is we are enhancing the greenhouse effect. We have enhanced the greenhouse effect by adding more of these greenhouse gases. We're going to see if we can do something a little more mathematical with that in the fifth part of this lecture. But first, let's do a couple quick questions. Question 9. What does the word monochromatic mean? Does it mean A, for radiation at a particular wavelength? B, for a particular gas in the atmosphere? C, with respect to height in the atmosphere? Or D, at a particular moment in time? We kept using this word monochromatic with words associated with radiation, like absorptivity and transmissivity and so on. The monochromatic transmissivity or the monochromatic absorptivity. What does that monochromatic mean? Make a choice from those 4 options and get a little feedback before you move on to question 10.